Okay, hello everyone. So this is a session which will focus on STP. After we've covered layer 2 Ethernet switching, we've also covered VLANs with the last topic that we did. With this one, we look at STP principles and configurations. So quickly going through this. On Ethernet switching, network redundant links are used to implement link backup and enhance network reliability. However, they produce loops leading to broadcast storms in an unstable MAC address table. So basically for the introduction, you're going to realize redundant links are very important in a network. They sort of provide backup, I think, in its simplest form. However, with layer 2 switching, Ethernet switching, they cause problems where we have what we call loops which may lead to what we call broadcast storms, which can potentially halt the whole network because you'll be having a lot of traffic, unnecessary traffic in a network. So when we talk of redundant links, it's just basically backup links. So if I can give this, for example, let me see. When we talk of redundant links, if I have a switch, if I have a setup like this, we have a redundant link there. Because if I have switch A, B, C, I have two links that leads me to switch C. So path one and path two, both of them they lead me to switch C. That basically means one of the two links is redundant. So having two links that leads to the same destination is okay. It provides backup. If this link fails, I can go via this one. If this one fails and this one is up, then I can go via one. But like I said, they have problems, and their problems are solved by what we call STP, and that is what we are going to be discussing today. Objectives, we're going to describe the causes of layer 2 loops, the concepts, working mechanism of STP, distinguish between STP and RSTP, then complete basic STP configs. That objective, I think we'll look at it on a separate lab, separate from these sessions. Then lastly, understand other methods to eliminate layer 2 loops. Technical background, redundancy in loops on a layer 2 switching network. So here we have, there is only one aggregation switch, no redundancy available. Right, here we have a typical example where we have, on this end, we have no redundancy here. Here we have redundancy. So if this link fails, like I was trying to explain, then we no longer have connectivity between our two switches, the aggregation and the access switch. But with this one, we have redundancy with this one because from this switch, from the access switch, you can go here, you reach the aggregation, you go here, you reach the aggregation, or you can go here, you get to your aggregation switch. So we have what we call redundancy. However, they create what we call loops. And by definition, what we call a loop is basically it's sort of it's by definition it's sort of a circular path. I think you can see from the symbol that is being used there. It's sort of a circular path that causes my frames here, all our data frames to continue moving in a sort of a circular motion. So in this example, if you get a frame which starts from this one, it gets to this switch, it gets forwarded to this one. It comes back, it goes there, it comes back, it goes there. That's where the circular path comes from. So a loop, if you have a data frame, if you have information that is continuously being directed in a circular motion, that's a problem. That's what we call a layer 2 loop. What causes that? One, we have causes by human error. So if you take a look at this one, basic configurations can create a loop. But with this one, we have number one, incorrect operations. Connection of cables between devices are incorrect. So if you take a look at this, right? If you take a look at this, there is our incorrect cable there. That cable basically creates a loop. We might not have a need to have that cable. However, if you're looking for redundancy, you might have need for that. But that causes problems, that causes layer two loops. Here, this is another example where you have two connections on the same switch. So if you have two connections on the same switch, that's not a problem if you bundle them. If you bundle them logically, we'll talk of Ether channel, I think, in future chapters. If you bundle those two, form an aggregation link, then that's not a problem. But if they behave as two separate links, then you're going to create a loop where packets will be moving in a circular motion. Data frames, not packets. We don't have packets at layer two. So that's basically one of the things that causes loops. Uh, Once we have loops, what comes with it? So, in summary, what causes loops is trying to have redundancy. In a network, if you're trying to have redundancy, which is good by definition, you're going to have loops. What causes those loops? Number one, we have what we call broadcast storms. So, a broadcast storm is a situation where in this example, when switch 3 receives the BUM frames, when we talk of BUM frames, those are broadcast unicast, broadcast unknown. Let me check. I'm getting a couple of messages. Right. Right. So if when switch 3 receives a BUM frame, this is a broadcast unknown unicast. So we have from this let's say from this PC1 position 1, we receive a BUM frame which needs to be broadcasted. Once that frame gets here, it gets broadcasted like that. Broadcasting is sending to all ports except the incoming port. If this broadcast gets here to this switch, this one, it gets here, it also gets broadcasted. So it also be sent here. If this one gets to this switch, it also gets broadcasted to this one. So now you have a situation where this is the same frame basically. It's the same frame which is being broadcasted. When it gets to here, it gets broadcasted again. Then we have my broadcast in a network. They will never stop. So here we're just considering one broadcast. If you have multiple broadcasts in a given network, that's a problem because that could potentially exhaust network resources on a given network, leading probably to a halt to a network. Performance gets affected. That's the problem with layer 2 loops. They create what we call broadcast storms. Then number two, another situation, we have what we call MAC address flipping. So in this example, MAC address flipping is basically where you have the MAC address of a given port being constantly changed because of these loops. Example, here we have a frame coming from this source. It's also a broadcast frame, right? When it gets to the switch, it will get broadcasted like this. This switch in its MAC address table learns about source MAC addresses. That's how a switch learns about MAC addresses. So it learns about source MAC addresses, then USM MAC address table. In this example, this one coming from this end, source pana port irir, inovayesa MAC address table irabai. Let's call this MAC address A. So MAC address table munomaiswa A, rovaranzi rikuya port G001. Right? That's how this switch learns about MAC addresses on specific ports. However, since broadcast rayani kuno, MAC address table switch learner as well, then it's going to register on this end another entry A Reaper G002. It's the same source but on different ports. So this is a problem. This is what we call MAC address flipping. This is a problem in networking because if, let's say, you want them to send something to MAC address A, which port are you going to use? Are you going to use this one, or are you going to use this one as the egress? So two things that we have, if we have layer 2 loops, they lead to my broadcast storms, which exhausts my resources. We have MAC address flipping as well. Then to solve that, we have what we call STP spanning tree protocol. When deployed in a network, it calculates a loop-free topology. One port on the network is blocked to eliminate loops. So with STP, what we now have, we eliminate the loop. If we eliminate the loop, everything, no more broadcast storms, no more MAC address flipping. So in a typical example, here 3-mass switch that we've been using, we come STP, what it basically does, it blocks one of the port. Not forever, but temporarily blocks this one. So this link doesn't work temporarily. So connection-wise, if S1 wants to communicate, if a broadcast is sent, kunok broadcast harikwanise kuuya because this link is blocked. Broadcast rikauya kunoko harikwanise kuuya ukoko because this link is blocked. So what STP does, it temporarily blocks a link. Here we have, I think what it looks like. We no longer have this link rip up. Physically, the link is still there. It's actually very functional, but it looks logically as if it is eliminated. Why? To eliminate my loops. Now, the beauty of STP in an event, let's say link is down. Redundancy here, we always have it with STP. Why? Because STP knows smooth the link ready. We unblock this one, block. Now we have a network functional. So STP basically breaks my layer 2 loops. And how does it do that? No block my redundant loops by blocking one of the links. How does it block it? That is what we are going to be looking at basically. There's a process on how it knows which port to block, etc., etc. STP can dynamically respond to network topology changes and adjust blocked ports. I think that is basically what we were discussing. So in this case, we have a blocked port. If we have a link fault, the blocked port is restored. Why? So that our network keeps working basically. So in summary, STP can adjust to network changes. Layer 2 and layer 3 loops. Layer 3 loops, common root cause routing loop. Right, loops we don't only have them in layer 2 networks. We also have them in layer 3. However, with the layer 3 loops, we have what we call the TTL, time to live. We have a way, routers have a way of not having my loops. How does it work? We have the TTL field, which basically decrements every time, every hop. So let's say I have a packet ripping up. Let's call this router 1. I have a packet up. A packet rene a field runs TTL. Let's say rene a number which is 4. Our TTL starts as 4. All right, that's the number at TTL. Every time I end up on the next router, this number decreases. 3, up 2, up 1, up 0. But when you 0, that packet gets dropped. If that packet gets dropped, it means we no longer have a loop. We have basically broken the loop because of the TTL field. So with the layer 3 looping, that can be prevented because we have TTL, which basically decrements every time you have a hop up until it reaches zero, then the packet gets dropped. Layer 2, we don't have a mechanism like the TTL, time to live. We don't have that. So you see, frame can continuously stay in this loop. If you have redundant links, if you have a loop, a frame continuously stays in the network anymore because we don't have TTL. So to solve that, that's why we have STP. So we have layer 3 loops, we have layer 2 loops, but with layer 3 loops, not much of an issue because of a mechanism what we call TTL. Application on a campus network. This is a typical campus network, and as you can see, we have redundant links. For me, switch 1, switch 2. To get from switch 1 to switch 2, there's a link wrapper. I can go via here, I can go via here. What do we call that? We call that redundancy. My links are redundant. My links are. These are redundant links. What comes with redundant links? Loops. What comes with loops? Broadcast storms. Broadcast storms, network performance is affected. So that's where we need STP. So STP, I think it's always be there in a network because we always have redundant links in typical networks. For example, that's a campus networks. They're just demonstrating there are redundant links. Therefore, STP is much needed. STP overview. STP is used to prevent loops. We've gone through this. Exchange with another device. Devices running STP exchange information. We'll talk of BPD use. After running a network, STP continuously monitors the network. When the topology changes, STP changes as well. Blocked links become active. With the growth and scale of lines, STP is very important. That's our overview. All right. Now let's start looking at some of the technical things with respect to STP. How does STP work? STP works by having some of these things. Number one, we have what we call the bridge ID. The bridge ID is basically an identifier of a switch in an STP network. An identifier of a switch in an STP network, and it is made up of what we call the bridge priority and the MAC address. So the bridge ID, it has two things. It is the bridge priority and it is the MAC address. Every switch on an STP, running STP, has a unique BID. So that's basically an identifier of a switch on a network that is running STP. My priorities edu, they range from 0 to 65,535. This should be 2 to the power of 32, I think. 2 to the power of 8, 9, 10. Yeah, this is around 32. 24. Not so sure. But it's 2 to the power of something. I think the actual number, it has a 6 here. But this is the range of my bridge priorities edu. The lower the bridge priority, uh, the higher the priority uh, when we are choosing the root bridge. So this bridge ID becomes very important when we choose yet not the root bridge. I think we'll get to look at that, Bamberi. We have what we call the root bridge. So in an STP network, there's an election process in it. You need to get to choose what we call the root bridge. How we choose the root bridge, we compare my bridge IDs. So we compare my priorities and my MAC addresses. The one with the lowest bridge ID becomes the root bridge, which is very important, identifying the root bridge. So the bridge ID is used to elect the root bridge. The bridge ID is used to elect the root bridge, and it is made up of the MAC address and the bridge priority. Bridge priority in my values in this range, and they come in multiples of, it's actually 2 to the power of 16. They come in multiples of, it should be 4096, I think. So you're going to realize the bridge ID, you have 0. Priority, I mean bridge priority, you can have a value as 0. You can have a value 4096. Then you can have a value 4096 times 2, etc., etc. I want a bridge priority value either 1, 2, 3. They come in multiples of 4096. I think this will become very important. Or default priority, also very important to know default priority, 32,000. This number. So this is the default priority. By default, my switch is here to at this value. By default. If I have two switches, the other one in a priority is 0, and the other one, this is switch 1, the other one in a priority here, 32,000. This one in a 0E becomes the bridge ID. That's the idea around becomes the root bridge, I mean. That's the idea around using my bridge IDs. In a case where you have my bridge priorities, they are the same, then we go and compare my MAC addresses. I think we're going to do that in practice. So you get a case, for example, let's say this bridge priority is 32,768 default. This one is also 32,768 default. If you compare these, they are the same. Therefore, you cannot elect the root bridge. You then go and look at the MAC addresses. MAC addresses will never be the same. They're always different. So in this example, bridge ID will become this one. So let's say this is also 32,768. From a MAC address, we have 4096, 4C1F, the same, AABC, then 102 ABC. Ish, no lowest in A. That's the lowest MAC address we have. Therefore, switch E don't change that, not the root bridge. It's just an election process. So basically, that's it with the BID. The BID is an identifier of a device, of a switch in an STP network. From there, we use the BID to choose the root bridge. What is the root bridge? The root bridge is the focal point of all STP calculations that we have. So for us to see which link are we going to block, it starts by identifying the root bridge. So to identify the root bridge, you are going to see all traffic will come through the root bridge, network made. That's how we prevent maloops, basically. So number one, the first thing you have to do in an STP network, it's not exactly what you have to do, but it's what the network does. It identifies the root bridge. The root bridge is the root of an STP network. After STP starts to work, it elects the root bridge. On STP networks, the device with the smallest BID accesses the root bridge. Smallest BID, root bridge. What do you compare first when you say smallest BID? You look at the priority first. By default, 32,768. Then, if they're equal, you look at the MAC address. The one with the smallest becomes the root bridge. During BID comparison, devices first compare bridge priorities. Okay, that's what we've talked about. The smaller the priority, the higher the priority. The smaller the priority value, the higher the priority. That's a bit confusing, but it is what it is. If priority values are the same, the switch with the smallest MAC address becomes the root bridge. We've gone through that. Then we have another concept, cost. When we talk of cost, this is a value which is assigned to specific ports to determine which path it should use to get to the root bridge. Right. Once you've identified root bridge, then you need to identify what you call the root path cost. The root path cost is sort of a cumulative value of all the costs, of all the port costs. So in this example, if you take a look at this one, let's say we have identified the root bridge right in the east. We've compared my BIDs and my bridge IDs, and we've identified root bridge. Now, we need to see to get to the root bridge, the lowest cost in the copy. So in this example, if I take a look at switch 3, port cost is up 20,000. Repanapa is 20,000. Basically, for me to get to this switch, it costs me 20,000. Right. For me to get to the root bridge via this direction, it cost me 20,000. For me to get to the root bridge via this direction, it cost me 20,000 here, then another 500 in Panap because of this cost. So ndikaenda so is 25,000. That's the root path cost. Ndikaenda so is 20,000. Why are these values important? Ndo atichashandisa kubloga malinks. Ndo mavalues atichashandisa kubloga malinks. Kune lowest root path cost ndo kune link risingablogwe. So in this case, if I'm to block a link from perspective ya switch 3, I can block this link because ndo kune cost yakati kurei. But I think on this slide, we just wanted to define what the cost is. The cost is a number which is given to a port, which basically determines how easy it is to get to the root bridge. Then the root path cost is now a cumulative value of all the port costs until I get to the root bridge. So, like I said from this example, port cost yangu is 20,000. That's the port cost. Then the RPC is also 20,000 because it just cost me 20,000 to get this one. But the RPC on this direction is 20,000 tap up, then another 500 tap up. Is that 25,000? No, that's 20,500. But it is what it is. Higher port bandwidth indicates a smaller cost. So my path, my links, and a more bandwidth costs in Engerishom. It means they are always preferred my links one. These concepts will also apply. They also apply. I think we did OSPF. There was an issue to do with my cost per OSPF, but my metrics. My metrics. Some of the things we define bandwidth as a metric, which then represents the cost your link. The higher the bandwidth, the lower the cost. The lower the cost, the more preferred link Iroro is. So basically, it's sort of the same concept here. Cost, we have port cost, we have root path cost. That's a summary of some of the costs that we have. Right, if you have a link 100 megabytes, a full duplex, then cost yako is 18. Kana tiri ku STP. Then is this value IEEE 802.1T. Not sure with what the standard is. Huawei legacy devices is 199. Let's focus on these ones. Let's focus on this one, the OG STP, these values. I think they are very important at this point. All right, so what you're looking at are default costs for specific ports. Can only port 100 megabytes per second. Rine full duplex, cost yacho 18. Rikaenda pa gig, cost yacho you can see reduce, ya 4. 10 gig, cost you reduce, ya 2. 40 gig, cost ya 1. 100 gig, cost is still 1. So the lower the cost, the more preferred the link is. So port cost yangu, port bandwidth yangu, port speed, kana iri very low, bandwidth yangu low, it means cost yangu is a bit high. That's the relationship between the port cost and bandwidth. I think basically that is what we are looking at on this one. Root path cost, I think that money we have already defined this one. Root path cost is the cumulative value of all the port costs. So ndikabva pa switch 3 ndikada kuenda kunoko. They haven't looked at it. Cost yangu RPC is 20,000. Ndikabva apa ndikaenda nekunoko. Okay, they're doing it the other way around. So ndikabva apa ndikauya uku kuti ndisvike panapa. The cost is 500 plus 20,000. That's how you find the RPC. By definition, RPC, just the cumulative value of all the paths, of all the port costs in a given network. I think I've missed on something that is very important here. I'm seeing it now. Also very important to recognize that patakaita OSPF. Port cost, path, port cost, it can be calculated. These are the default values, but it can be calculated. One, it can also be manipulated. You can manipulate, could even port rako the speed 100 megabytes per second, right? 100 megabytes per second. You can make that port have more, be much more preferred than one runner 10 gigabyte per second. How do you do that? You can manipulate my values. So cost in a definition, in a formula, is equals to what we call the reference bandwidth over the port bandwidth. Right. Cost is equals to reference bandwidth over the port bandwidth. Reference bandwidth, this is usually in C. In Cisco, I think it should be 100 megabytes per second. Right. So iwewe ukawuya ukamanipulate this value ish, you can basically manipulate my cost. Ukawuya ukachange this value. This value can be changed on my device. You can change the reference bandwidth. So if you come and we manipulate this value, you can basically change and manipulate my costs, change how the network will behave basically. You might have a preferred route or whatever. So you can manipulate the network to use that preferred route. How do you do that? You manipulate my values A, the reference bandwidth, because cost, it is a formula in none. It's also the same thing which is used for OSPF, like I said. I think my metrics, a bandwidth, which leads to cost, they're very important. OSPF as well. That's how you manipulate those values. RPC, we've gone through that. We have the PID. Is that the port identifier? Probably. The PID, it identifies ports and very useful tie breaking. Yeah, these ones are best explained by my examples, right? But basically, port ID is a port identifier. My values actually the range from 0 to 240, and my intervals is 16. So here my port IDs, they range from 0 to 240. And my intervals is 16. So you can have 0, 16, 32, change that. Okay, multiples of 16, I think it works. My identifier is specific ports. Specific ports. A port is identified. So you're going to realize with the process STP, tatangira ku, we need to elect the road bridge. How do we elect the road bridge? To change a bridge ID. So the bridge identifier relations of election process. We get to a case where my cost edu can be the same per network. It's also to that one which is the one innate to the road bridge, but as to one akafanana. How do we then separate them? We use the PID. At some point, you're going to be using PID to separate Panama cost and akafanana. That's where this comes in, the port ID. For now, I think keep in mind the values, they range from 0 to 240, multiples of 16. And we're going to use application, I think, to understand more what the PID is. BPDU, Bridge Protocol Data Unit. So here, these are the data packets for STP. This is what carries STP information. Network yedu, at the initiation stage, network yedu, Parantangira network yedu, there's an exchange of BPDUs. My BPDUs carry information in STP. For example, switch 1, 2, 3, I square on. They send my BPDUs. My BPDUs, they contain information. Most importantly, you go to inini. My bridge ID is this. So every switch shares its bridge ID. By election process, zero my bridge IDs, then compare my bridge IDs. After comparing, then choose the road bridge. So the importance of the BPDU is the packet which contains information in STP. Could what's the bridge ID of specific devices? Panotika topology changes, ndo inokera that information with the change ID. So it means we need to also change um, the network basically. So two types of BPDUs that we have: configuration BPDUs, then TCN, topology change notifications. Configuration BPDUs do are exchange via anima BID, then practical change we have a TCN. I think very simple concept. BPDUs. 3 minutes. Format of BPDUs. This is the format team of BPDUs, Edu. I think we've gone through format here, Ethernet frame. Your SFDs, your preamble, your source mark destination type, payload, FCS, error check, etc. That's the format. I think we've also gone through format the IP, the packet. Matthews Anna TTL, for example. We've also gone through, did we do the segments? I don't think we did. But here we are looking at format PPTU. My formats becomes very important. Knowing what my fields are now per BPTU, for example, I say. So these are some of the fields. Those report message that I discussed already. Port ID, report BPTU. Basically, changes do BPTU. Yes. Bridge ID, type discuss, report BPTU. RPC is also information in report BPTU. Hello time. We'll get to discuss it, but very important. This is report BPTU. So you need to know my fields are report BPTU and what information is carried in that field, and why is it important to give that information? Right. I'm not going to go through all of them, but I think as we proceed, we'll discuss them. We'll definitely look at this one, this one, this one. Not sure this one. Port ID, we'll look at this one. Bridge ID, we'll look at it. We'll look at this. We'll look at this. My flags, I will look at them. PPT type, not sure. These two, I think we'll partly look at them because they are as important. Right, I can see my time is less than 1 minute. I'll share another link. Then we have our last session of the day, of the morning, not of the day.